Welcome to the Globe, welcome to CERN, welcome to CERN's open day, and welcome to our Hadron Cafe. For the next 30 minutes, we're going to talk to you about antimatter, we're going to show you some experiments, and there will be some more music. It's 30 minutes long. Please stay with us. Don't leave halfway through, because it creates a big mess. Okay, restez avec nous pendant 30 minutes. Merci beaucoup. Okay, antimatter. We're going to talk about antimatter. We have an expert on antimatter here with us today, Rolf Landua, my friend and colleague, who's worked in the field of antimatter for more than 30 years. And he's still alive. But I'm definitely not going to touch him.
Careful.
Okay, Rolf, what is antimatter?
Well, I mean, first of all, maybe it's useful to say what matter is. So matter is made of very small particles, which we call the electrons and the protons and the neutrons. The protons and neutrons themselves are made of quarks. So that's so far as we know what matter is. Now, antimatter is basically a mirror image of this matter. So you take, for example, the electron and you change its charge from negative to positive. And then you have antimatter. Has the same mass but a different charge. The only strange thing is when you bring matter and antimatter together, then it disappears into a flash of energy. So if we had a table made out of antimatter and a table out of matter, we bring the two together, they disappear.
Okay, and how do we make antimatter?
Well, to make antimatter, you have to take energy and you concentrate this energy to a very, very tiny volume. So you have to create an extremely high energy density, which we can do when we collide particles. When we collide particles which themselves are very, very tiny, and they collide, then this energy, which was in their movement, is converted into something new that did not exist before. Every time we produce something new that did not exist before, we create matter and antimatter, equal amounts.
Do we make antimatter at CERN?
Of course. That's what we have been doing for almost 40 years now at CERN. And I have been leading an experiment which not only made antimatter sort of particles like antiprotons and anti-electrons, we brought them together to form the first atom, the first anti-atom, which is anti-hydrogen at very low energy.
Okay, now why on earth would we want to do this?
Well, of course, what I just said about the creation of antimatter, when you concentrate energy on little space, that is very much similar to what happened at the very beginning of the universe. The universe came out of a tiny speck of energy, of course lots and lots of energy, was in a tiny space, and when this point started to expand, this energy also transformed into mass, particles, but equal amounts of particles and antiparticles as far as we know. And the question is, when we look out into the universe nowadays, we do not see where all this antimatter is. It seems to have disappeared, and we wonder why. And in order to find out what the reason is, we do these experiments to study very precisely the differences, if there are any, between matter and antimatter.
So how much antimatter can we produce at CERN?
Well, much less than people think. Sort of one atom is very, very tiny. That's 10 to the minus 24 grams. Okay, that's very, very little. And even though we produce large numbers of these tiny particles, something like 10 to the 14 or 10 to the 15, altogether in a year we can make a billionth of a gram.
In 1 year we can make a billionth of a gram, and CERN is 54 years old?
Right, and we haven't done it all over the time, and we cannot really store all that antimatter. So we do not really have any antimatter in our sort of vaults anyway.
So when Dan Brown writes in his book Angels and Demons that somebody can steal a gram of antimatter at CERN and possibly blow up the Vatican, this is not true?
Not quite, no. We have excellent relations with the Vatican, I have to say. So we do not intend at all to do any harm to them, especially not with antimatter, which we do not have. Even if we tried to do it, we couldn't. I mean, it would take 1 billion years to make a gram of antimatter, so that's a bit long. And also it would cost a lot of energy. It would cost much more than about 1 billion euros or something like that. So it's a bit expensive.
However, I believe that the filmmaker who produced the first film of Dan Brown's second book, actually, visited CERN not so long ago, and they are actually going to make a film about angels and demons. Will CERN appear in that film?
Yes, of course. I mean, we play one of the main roles. So they will come here to probably do one scene of the movie. The rest is done in London and in Rome. And, well, we had a long discussion over the whole day how we can make it at least plausible that you can make this 1 gram of antimatter, you know. So we had to cheat a little bit in the technology and also in the physics. But it will come out probably quite reasonable in the movie, I hope.
Okay, but the real answer is that we do not have an antimatter vault somewhere which somebody can break into and steal enough antimatter to blow up the world.
Right.
Okay, talking about blowing things up, we have here a team of young physicists from Zagreb, from Croatia, and they're going to do some experiments for us. So big thank you to these guys from coming all the way from Zagreb.
Thank you very much. So we won't blow anything up, but we will implode something up, sorry. So my friend here has this bottle of Red Bull, but there is a small amount of water inside, which is partially evaporated because we heat it up. And he will now put it in water. And you can see the container imploded really fast. So another one.
So why does it implode?
So inside we have evaporated water at 100 degrees Celsius. The water that we put the container in is roughly 25 degrees. So we basically cool down the evaporated water really fast. The cool down air inside will have lesser volume than it had when it was evaporated. So it will create vacuum that will suck in the sides of the container. That's why it implodes. So here we have a glass bubble, and I know you will say that water evaporates at 100 degrees Celsius, and we saw that it evaporates at 100 degrees Celsius, but I will make it boil, or we will make it boil at 25. So let's see. Why will it will start to boil? Because we get air out. So inside there is vacuum, or close to vacuum, and you can see here something white that's come out. That is vapor of water, and when we put inside the water, there are air bubbles that can't go out because of the pressure from our atmosphere. And when we pump out the air, there will be no atmosphere inside. There will be no force on the water, and those bubbles will be able to come out. You can see it over there.
So the water is actually boiling?
Yes, the water is actually boiling at 25 degrees Celsius. And we will prove it by... Okay, so we can't lift it now because there is no air inside.
But somebody tells me this is why in Tibet there's no point in ordering a boiled egg for breakfast.
Yes,
because you can't boil an egg.
Yes, yeah, that's correct, because the proteins coagulates at about 60 or 70 degrees, and you would have to expand the whole canister of gas to boil an egg on 8,000 degrees, 8,000 meters of height.
Got one more experiment?
Yeah, one more. Here we have a balloon that is filled with ordinary air, and we'll put it in liquid nitrogen that is at minus 200 degrees Celsius, completely inert. And you will see that the balloon starts to shrink. That's because the air, when cooled down, it has lesser volume than when it's at normal temperature, and that's why the balloon starts to shrink. And as it hots up again, the balloon starts to become more and more, starts growing.
Okay, thank you very much. Big round of applause. Not easy to do experiments online like this. Thank you very much for our team from Zagreb. Now, in 5 minutes, you're going to have a opportunity to ask your own questions about antimatter to Rolf. So, while we listen to Exil play again, think of some questions that you would like to ask Rolf. Vous pouvez poser les questions en français, bien sûr. Exil.
This is called Just One Illusion.
Qu'est-ce qui te fait courir après un autre toi-même pour que tu t'aimes? Hey! Qu'est-ce qui te fait nager contre l'essence du temps pour au fond patauger dans le contre-courant? Qu'est-ce qui te fait vouloir posséder, entraîner toutes ces images volages dans ta propre cache? C'est juste une illusion, à peine une sensation qui dirige tes pas et te montre du doigt où tu vas, où tu vas. C'est juste une illusion, comme une bulle de savon qui s'approche de toi, que tu touches du doigt, puis qui s'en va, qui n'est plus là. Hey! Où puis-je aller maintenant, sans te donner l'idée qu'on est revenu de tout, que c'est pareil partout, et notre secret tout en dehors court dedans. Tout ce que tu vois dépend tellement de ce que tu sens. C'est juste une illusion, à peine une sensation qui dirige tes pas et te montre du doigt où tu vas, où tu vas. C'est juste une illusion, comme une bulle de savon qui s'approche de toi, que tu touches du doigt, puis qui s'en va, qui n'est plus là. Le nez collé à la vitre glacée contre ta tête.
Merci beaucoup, Exil. Thank you very much to the CERN Music Club for providing all the bands today. And before I forget, because I've only got one more session here, big thank you to all the technical team who've been here all day working very hard. So big thank you to you guys as well. Thank you. Now, it's your turn. Questions about antimatter. Kieran. Wait, just one moment, please. We have a microphone for you.
Thank you. I got two questions, actually.
Well, let's have one first.
Can we create in the future more antimatter?
Can we create more in the sense that we create many grams, or is that the question?
Yes.
Well, it's limited in part by technology that can be improved. So in some sense, we could think we can create a factor 10 or 100 more. But then there is a limit to create stable antiparticles, which are relatively rare. So there we're losing sort of basically about 1,000,000 to 1 in efficiency. And that cannot be overcome.
So the answer is not really. Okay?
Not much more.
Okay, next question.
So why is antimatter so unstable?
Well, it's actually not unstable. I mean, as long as you do not bring it together with matter, it is as stable as ordinary matter. So in an anti-universe, we could create everything which we see here. I mean, if there is one, it would probably look exactly like here. The only thing is when the two touch, when the two come together, then they annihilate. They will destroy each other into energy.
Okay, another question? Yes?
It's common knowledge that for all scientific experiments, there are potential civilian applications as well as military applications. Could you please give examples of some civilian applications and military applications for antimatter?
Well, the most common civilian application is in medical diagnostics. It's positron emission tomography. You're taking radioactive isotopes, you put it into glucose molecule, it's injected in your body, accumulates where some energy-intensive process takes place. For example, now you are thinking what I'm saying, so it would take place in your brain, and then with a detector around it, you can localize that spot where the antimatter from these things annihilates. So that's something which has every hospital since 1974. CERN was actually involved in this development. I mean, there's lots of others, but I go now to the question about the military you want to know. I mean, they have been thinking about it in the 80s, but once they realized that it's extremely expensive and extremely unpractical to produce large amounts of antimatter, and for us, large is anything beyond a billionth of a gram, they gave up.
Hi.
Okay, another question over here. Oh, sorry.
So my question is, how do you...
Where are you? Could you stand up, please?
I'm over here.
Oh.
Yeah. So how do you stop antimatter from annihilate with matter? How do you keep it contained?
Well, two elements. First of all, you have to keep it away from air. So you have to pump all the air out of a little storage trap, which we call it, so that it doesn't meet any ordinary matter in there. And in order to contain it, we use electric and magnetic fields, which force it to stay where we want it to stay, because it's sort of repelled by certain electric fields and forced on a circular trajectory by magnetic fields.
Another question? Over here. Kieran?
You said at the beginning that at the beginning of the universe, when this Big Bang happened, that matter and antimatter was there in an equivalent volume. Would now in our universe, would all the electromagnetic energy, all the radiation that is out there in the cosmos, balance the volume of antimatter that existed then?
We think so. I mean, the process was that Probably there was 50-50 at the beginning. Then most of the matter and most of the antimatter annihilated, I mean destroyed each other and produced electromagnetic radiation. And nowadays, and a little bit was left over, that's us and all the stars, the galaxies and so on. And nowadays when you look into the universe, you find for each particle we are made of, we find about 100 million or more light particles, photons, which came from this big battle between matter and antimatter. Now, why this happened and why there was this little asymmetry, we don't know, but one of the experiments here at CERN tries to find out.
Yeah, you talked about the PET imaging and that it's very difficult to produce and maintain antimatter. Then how does it work? I mean, and why doesn't it have a reaction with the matter?
Well, every time we make antimatter, we do it in a brute force way. Basically, we shoot particles onto a little block of metal. I mean, you can also put your finger in, but it's not good for your finger. Shoot it on a piece of metal, and in these collisions, we produce all kinds of things, new things, which were not there before, and some of them are antiparticles, which we can then sort of guide through magnetic fields into a special tube, which is basically kind of an accelerator. And there we can store it without it touching any matter. And we manipulate it by electric fields. So it doesn't touch anything, and we just keep it with electromagnetic fields.
Okay, thank you very much. That's unfortunately we have no time for any more questions. Thank you very much for coming to CERN today. Thank you for visiting the Globe, and thank you for participating in this Hadron Cafe. If you would like to stand up and leave that way. Thank you, Rolf.